All right, welcome students to lecture 14. This is the second part of chapter 8, the chapter that deals with gases. For this, remember you should be reading sections 8.4 to 8.7 out of the Timberlake textbook. There will be 4 sections to this lecture. First, we will dive into Gay-Lussac's law, another law, this time dealing with temperature and pressure changes. Then we will go and explore Avogadro's law. His name is familiar, right? So it's the same person, but he also studied gases, and he studies the relationship between moles and volume of a gas. Then we will combine all the laws that we've learned so far into something called the combined gas laws. Then we'll end our discussion in this chapter with what is known as Dalton's law, and he talks about the partial pressure of gases. First, let's discuss Gay-Lussac's law. To explore this idea, let's take a look at this sample of gas molecules in a container. There are molecules of gas as seen here, so there is a value for the moles. This container has a certain volume and a certain pressure, and also it is being heated by that candle on the bottom there. Okay, so we can call this state 1. And so far we can measure, let's say we can measure that it has a temperature of 200 Kelvin and a pressure of 1 atmosphere. Let's see what happens when we change a few factors and we call it state 2. Take a look at this representation. Can you see what has changed? Of the 4 properties of a gas, what has changed? Most obviously, this flame, correct? This flame got bigger. This flame that is bigger represents that the temperature has increased. Okay, so we call this state 2, and we have doubled the temperature to 400 Kelvin. Okay, now using kinetic molecular theory, can you explain what will change if temperature increases and volume doesn't increase? Notice that the volume of these two are the same, and the amount of gas molecules hasn't increased, so its moles are the same. So the only thing left is pressure, right? So using KMT, how will pressure change when you increase the temperature? Hopefully you were able to say that the pressure will also increase. Now, how does that work? Notice that when temperature increases, the molecules move faster because it has higher kinetic energy, right? So if it moves faster, it will hit the wall at a higher frequency and also with higher energy because it is moving faster, higher kinetic energy. Because of that, hitting the wall much more frequently and a higher impact, its pressure then also increases. It increases in this case to 2 atmospheres. It exactly doubles, right? So if you double the temperature, the atmosphere also doubles. Again, we call that direct relationship. When one increases, the other also increases. Okay, now, so if let's say we decrease the temperature, you would predict that the pressure would decrease. Very good. So let's take a look at this from a mathematical perspective, like we've done with the other 2 laws. Let's say that we would take temperature and we divide it by the pressure. We get a certain value. That's, in this case, 200 Kelvin per atmosphere. That's the state 1. Let's try to do that again for state 2. We do that again for state 2. We see that we also come up with 200 Kelvin per atmosphere. So it turns out whenever you take temperature divided by pressure, you will always get the same number. Okay, so T2 divided by P2 is a constant number. T1 divided by P1 is a constant number. Since they are equal to the same number, mathematically that means T1 over P1 is equal to T2 over P2. So that's our relationship, and we call that Gay-Lussac's law. Okay, now as always, this is a fraction in an inequality, so we can always say the flipped is also true. We can always say that pressure, we can put pressure on top instead of temperature. We can say that pressure over temperature in state 1 is equal to pressure over temperature in state 2. Okay, so either of these laws will be useful. Remember, we want to use the law that is most helpful for us when we rearrange the equation. Okay, so let's do an example using Gay-Lussac's law. This example reads, a rigid container of hairspray at pressure 4 atmosphere at room temperature, which is 25 degrees Celsius, is thrown into the fire, which increases the temperature of the gas to 402 degrees Celsius. What is the pressure in a hairspray at the elevated temperature? So we're asking to find the pressure, right? And it also says here at 8 atmosphere, there will be an explosion. So it's kind of cool to see what atmospheres we get and whether we will get an explosion or not. So let's go to the board to do this problem. All right, so the way again to tackle these gas laws problems is to state and write down what you know. Let's read the problem. Again, a rigid container of hairspray at pressure 4.0 atmosphere. Okay, so that's our first pressure. So we say that P1 is equal to 4.0 atmospheres. Okay, at a temperature of 25 degrees Celsius. So that must mean that T1 is 25 degrees Celsius. But remember, for gas law problems, we cannot use Celsius for temperature. We have to first convert everything to kelvins. That's just a matter of adding 273 to this number to give us our Kelvin of 298. Let's continue reading the problem. It is thrown into the fire, which increases the temperature of the gas to 402 degrees Celsius. Okay, so that gives us that the second state has a temperature, and that temperature is 402 degrees Celsius. Again, converting that, we get 675 Kelvin. So then, what is unknown is our P2. Okay, so since we are solving for P2, I'm going to choose the equation that has P2 on top. And the equation that has P2 on top then is P1, or P2, whatever, P1 over T1 equals to P2 over T2, right? So again, we need to isolate P2. So to do that, we multiply both sides by T2. When we do that, notice that T2 and T2 cancels out, so you can erase them. Therefore, it gives us a relationship that P2 is equal to P1 times T2 divided by T1. Okay, so now we just plug it in. What is our P1? P1 is 4.0 atmosphere times T2 is 675 Kelvin. Divide that by T1, 298 Kelvin. Our unit analysis tells us that the Kelvin and the Kelvin will cancel out, giving our answers in atmospheres, which makes sense because pressure is indeed in atmospheres. If you do that in your calculator, you should get 9.06, but how many sig figs do we get? 1, 2. So that becomes 9.1 ATM atmospheres. Okay, so that's how you do that problem. All right, so let's now do the checkpoint problem. Again, using, or not using, but when we see gas laws, we want to state out all the variables. Reading this, it says the fire extinguisher has a pressure of 10 atmospheres. Okay, that's our first point, data point there. So that must be P1 is equal to 10.0 atmospheres at 25 degrees Celsius. So that must be T2. T2 is 25 degrees Celsius, which is 298 Kelvin. What would be the pressure if the temperature is now 75? So that's our T2. 75 degrees Celsius is 348 Kelvin. Okay, so again, this problem is very similar to what the one we did previously. What we're looking for is P2. We already solved for P2 in the previous case, so just use that. So P2 is equal to P1 times T2 divided by T1. plug it in. P1 is 10 atmospheres. T2 is 348 Kelvin. T1 is 298 Kelvin. Again, notice here Kelvin cancels out, giving you atmospheres, and you get 11.7 atmosphere in your calculator. That gives you the answer, letter B.